Hi everybody, in this video we are going to be talking about unit 9.3.1, which is real numbers, associative, commutative, and distributive laws. This is one of those topics, it usually takes a little bit longer for students to kind of grasp the information. And so if you need to rewatch this video or you need to slow me down and put me on slow motion as I'm working through this, please do that. I would also encourage you to reach out to me if you have any follow-up questions, and I would be more than happy to address your questions. All right, so this first page is a bunch of definitions. So we're going to do that first. So this first blank is mathematical term. And a mathematical term, if we use that when I say how many terms are in this expression. An expression you're going to see is another one of our definitions. But let's first talk about what is a term. So a term is a number or a variable or numbers or variables that are multiplied together. They are also terms that are separated by mathematical operations. So for example, like if we're saying they're a number or a variable, so it could be like this, 5, that's a mathematical term. X, that's a mathematical term. We could have 5 plus X, and that would be an expression made up of 2 terms. We would have the 5 term and then the X term. We could have 5X plus 2Y. And again, that would be a mathematical expression, again, still made up of 2 terms. We have the X term, and the coefficient on that X term is 5. And again, we're going to talk about what is a coefficient right here. And then we would have the Y term, and its coefficient is 2, and it's right there. So all of these are considered mathematical terms. And sometimes I don't throw negatives in and then students are like, wait, it can't be negative. No, that's not true. It can be negatives. It could be a fraction. It could be like negative 3x squared plus 1/2. And then that is an expression also made up of 2 terms. You have your x squared term, and then you've got your constant term here at the end. Our next definition is variable, and a variable is a letter or symbol used to represent a quantity that can change. So we typically use X and Y most commonly, but any letter or symbol, like you could use a smiley face if you wanted to for your variable. So we might have something like what we did up above. We have 5X. That's a variable. So the X would be considered the variable. You could do negative 3xyz. And so the X, the Y, and the Z are all considered your variables. If we have something like area equals length times width. Whoa, got a little crazy with my W there. The L, the W, and the A are all variables because all of those variables can change. You can put in any value for it. All right, so then we've got kind of contradicting this or contrasting it, we've got a constant. So unlike a variable, a constant term is let me make sure I'm putting in the correct blank here, is a quantity. So if this one can change up here, that does not change, right? Because it's a constant. It does not change. And it's often a number. So we've got constants such as, like if we did this, if we got our area equals 1/2 base times height, that's the area formula for a triangle. So this 100% of the time, this is always going to be 1/2 because it's constant. It's a number that's going to be in there. We might have, if I go back up to my other example of 5 plus X, well, this is the constant right here, and the X would be the variable. We might also have like the irrational number pi. Pi would be considered a constant because pi is always going to be 3.14, and it's going to be that decimal that goes on forever, it doesn't repeat, so it's a constant, it's going to stay the same. A coefficient is a type of constant. So I want you to think about nesting baskets again. So if here's the set of constants like this, and then we have a smaller subset inside, and it's made up of coefficients. So for example, we might have something like, 2x would be a coefficient. It's also considered a constant, right? Like that 2 would be a constant. But then out here, if we had solely a constant, like if we had, let me write it up like this, x plus 2, that 2 is only a constant. It's not also going to be a coefficient. All right, so let's talk about that. A coefficient, how do those differ? A constant term is multiplied by a variable or variables. So a coefficient is what's directly in front of a variable because it's multiplied by that variable. And so, other examples, like if I was putting in 2x plus 4, here is your coefficient. Are these both constants? Is this a constant and this is a constant? Yes, but only this one is a coefficient. So this is a coefficient, and this would be considered a constant, and this would be a constant, again, because they're numbers. And that tells you that too. A coefficient is a type of a constant term. We might also have something like negative 1/2 x, y, z. So this negative 1/2 would be considered your coefficient. All right, so then we kind of compare, contrast, what is an expression versus an equation? What is an expression versus an equation? So an expression is a mathematical phrase made up of operations, numbers, and or variables, but it does not contain an equal sign. Does not contain an equal sign. So many of the things I've given you up above are expressions. So like this 2x plus 4, that's an expression because there's no equal sign. Negative 1/2 x, y, z, that's an expression. We could just have like 5 plus 2. That's an expression. There's no equal sign there. An equation is a mathematical statement. So you can think about this if you're an English person, like a fragment versus a sentence here. Our expression is similar to a fragment, and our equation would be similar to an actual statement or a sentence. So mathematical statement made up of operations, numbers, and our variables. Excuse me. And an equal sign. So I could take even what I wrote up above and I could say, well, 2x plus 4, and we'll just set that equal to something. Maybe it's like equal to 15. And then one up here, negative 1/2 x, y, z, and that's equal to 10. We could also do area equals length times width. That is one. Area equals 1/2 base times height. That would be another equation. So that's where they're different. So something else that you're going to see as differences in terms of their directions. For expressions, we usually say simplify the expression. And simplify means combine like terms. Simplify, again, typically is what's that saying, is meaning combine like terms, which is what we're getting ready to talk about. Combine like terms. So that's what we're going to talk about down here. And then an equation, the directions for that would actually say solve the equation. Solve the equation. So I just want to point something out. Can you solve an expression? No. You can't solve for a variable in an expression because there's nothing on the other side of the equal sign, right? Because there is no equal sign. Whereas this one, I could say, yeah, let's solve for x. We would subtract 4 from both sides, and then we would divide both sides by 2. And we're going to get to that. We're just not there yet. Anyway, I just want to point that out, the difference in the directions. So these equations usually say solve the equation. Expressions are simplify the expression. All right, like terms. What makes terms like terms or similar, like they're the same term? They are terms that have the same exact variables and exponents. And they can become combined together. They do not need the same coefficients, however. To be considered like terms. So for example, here's some examples. If we had 2x plus 5x, those are considered like terms. So you ask yourself, do they have the same exact variable? Yes, they're both x's. Are they raised to the same exact power? Are they both x to the first, x to the first? Yes. Therefore, you can combine them. So you would say 2x plus 5x, how many x's do I now have? I have 7x. So that would be your total. What about, here's a non-example. What about if I had 2x plus 5x squared? That's a non-example because yes, they're the same variable. They're both x's, but are they raised to the same exact power? No. One is x to the first, the other one is x squared. So the only thing that we would do is we would rewrite this in what's called descending order, which again, we're going to talk about down here more, but I'm just going to throw it out now, where we lead with the one that has the highest power. And so we would say 5x squared plus 2x. So we would just rewrite it and we would get that for our answer. Let me throw out a couple more examples. So another one, if we had, here's an example. If we had 2xy plus xy plus a negative 3xy. So again, you look across and you say, do I have the same exact variables? Yes, I have xy, xy, xy. And I'm going to do one more thing just so you know that it can change. I'm going to say that this is like x to the third y, x to the third, and I'm going to put x to the third on that one too. So I'm just going to add that in there. So you look, are they all xy's? Yes. Are they the same exact power that it's x to the third, y to the first? Yes, all the way across. So now you look at your coefficients and you combine them. So 2 and this, it's an implied 1. 2 and 1 is 3. So I would have 3xy, and this is going to be minus 3xy. Well, how many xy's are left? None. So it'd be 0xy, but do I write 0xy? Well, 0 times xy is just 0. So you can just write 0 for that one. Let me give you here another non-example. Another non-example. So let's say that we had a very similar one to the one we just had, and it was like 2x to the third y plus xy to the third plus a negative 3xy, like that one. So you would look across and say, and this is a non-example. So this is a non-example. You would look across and say, are they all the same variables? Are they all xy, xy, xy? Yes. Are they raised to the same exact power? Oh. And the first one is x to the third y. There is no other x to the third y's. You might look at the second one and say, wait, there's a third power, but that's on the y, so it's not the same. So you have 3 y's, and on this one, you only have 1 y. So none of them, if you look across, none of them are the same exact power. So then what we would do, and again, we're going to talk more about it down here, we write this expression in alphabetical descending order. So alphabetically, they're all the same. They're all xy, xy, xy. And then it goes in descending order. So we look at the x's, Which one has the highest power? This one. So we're going to start with that one. So I would rewrite it as 2x to the third y. And now I look at my next two and I say, okay, let me look at the xy to the third, xy to the first. Which one should come first? Well, it would be this one because it has the higher power on the y. So it'd be plus xy to the third, and then finally we would have minus 3xy. And that would be your final answer for that one if we were rewriting them in alpha descending order. And I know that one happened to already be in the same order, but we were able to simplify that plus and negative there. Okay, so let's talk about rules and or conventions for writing mathematical expressions. So one convention is we put coefficients before the variables. So we would do something like 5x, not x5. And x5, the reason why we don't do that is because it kind of looks like multiplied by 5, and we don't want to get in the habit of that. So we're always going to flip it around and write 5x. Also, we would not do something like x5y. If it was like that, we would use our commutative property and move 5 to the front over here and have it change places. All right, we have special cases though for this. 1x, we typically just write it as x. Is it wrong to write it as 1x? No, it's definitely not wrong, but we just typically write it as x. The next one, you saw me do an example of it right here. We usually leave out 0x because it's just the same as 0. Again, if you left your answer like this, is that wrong? Absolutely not. It's 0xy. 0xy is the same as 0. So both of those are correct, but conventionally, we typically just write it as 0. Our second convention, we write variables in alphabetical order. Alphabetical order. So, some examples, we would have x squared y z to the fourth. They're going to come in order. If you were given something like b, a, d, c, you had something like a big variable, a big term, mathematical term like that, we would rewrite it so it was in alphabetical order. And so we'd flip these two around, we'd flip those two around, and it would be A, B, C, D for that. Next one, we write terms with exponents in descending order. So for example, descending order means like if we have 5x squared plus 3x minus 2. So if we had something like that, they're in descending order. It's x to the second, x to the implied first, and then nothing. There's no x here. Let me give you another one. I'm actually going to mix this one up, and I'm going to have you guys see if you can put it in order. So we've got x, y squared z minus yz. And then we're going to do plus, let's do x cubed plus 2xy squared plus 5x squared y. All right, so let's see if we can check the alphabetical descending order. So alphabetically look at them. Within each term, they're in the correct order, x, y, z, x, xy, xy. So within each term, they're in correct alphabetical order. In terms of alphabetically, so first looking at alphabetical order, if we were putting these as files in a filing cabinet, which one would come first? Which one would be the very first term? And the very first term would be the one with just the x on it, right? So we're going to bump that one to the front, and it's going to be x to the third. So we're done with that term. The next one that I want you to look for, okay, so let's look at our terms. We've got xyz, yz, xy, xy. So the next ones alphabetically that would come would be these xy's. So now what we do, we look for the descending order part, meaning you look at the exponents on those variables. So look at the two x's. We're looking at this x and this x. Which one has the higher power? Which one has the higher exponent? And it's this one, right? So because it's 2 compared to this implied 1 on that x. So then we're going to write plus 5x squared y. So we're going to cross that one off. We're done with that one. But that means it's pretty easy. We know that this one's going to come next because we already know alphabetically it would come before this xyz term and this yz term. So we're going to write plus 2xy squared. Alphabetically, which one would come next, the xyz or the yz? And I'm hoping you're saying it right. It's that xyz term. So we're going to write plus xy squared z minus yz. And we are finally done kind of reordering that very long expression. All right, a lot of times I'll have students come up with all kinds of great what if scenarios after this example. So if you have some, check it out, like look at what we did here and write it down in the margins of your notes and then send it to me, like take a picture of it, text it to me, email it to me, talk with me about it in class or during office hours. Bring it to my attention and let's go through your what if scenarios on those because you guys come up with some really great ones for like, what about this type situation? Which one would come first? So send those what if scenarios to me. I'd be happy to address them. All right, so then we're going to talk about properties here. So we're going to talk about some properties. So the first property we're going to talk about is the commutative. A lot of times people will say that's the commutative, commune. We're not communing, we're commuting, which means changing places. So think about commuters. Like if you commute to work, that means you drive to and from work rather than working remotely, right? Like remotely, we're working from home. But commuting, we are driving to work and then we come back home. And then we go to work and then we come back home. And then we go to work and then we come back home. So you're commuting, you're trading places. So you can change the order in addition and multiplication problems in mathematical expressions, and the answer will remain the same. So for example, that means here's a very basic example. If we had x plus y, what would it look like to employ or to utilize or to use the commutative property? This is the commutative property of addition. Well, what it means is that these two variables can trade places over that symbol, which means then we get y plus x. So they're trading places. Well, why would we ever want to do that? Well, let's look at an example like this. Let's say we had 13 plus 22 plus 7. Here's a perfect example where it would make sense to say, oh, I think this one for mental math wise, it would be so much easier to go like this. Let's trade those two. And then, so we've employed the commutative property of addition. So that's why I'm putting C plus. And I am going to rewrite that. It's going to be 13 plus 7. I'm sorry, not plus 7 because I traded places. Silly. Oh, you guys, what am I doing? We did trade places, so that should be 7 plus 22. Thinking about what's coming next. I'm not talking and writing very well today. All right, here we go. So now what that means is take that. What's 13 and 7? You guys know what that is. That's 20. So then we take 20 plus 22, and now that becomes so much easier for mental math, and that's 42. So that's a perfect example where the commutative property, and I know a lot of times, like you're doing this in your head, you're actually doing this. You're thinking, okay, actually I could put together 13 and 7, and that's going to be 20 and 20 and 22, that's 42. And you're doing that commutative property in your head, you just don't realize it, that's what you're doing. All right, let's try another one. Here's of multiplication. All right, so if we're employing or using the commutative property of multiplication, what would that look like? Well, it just means we're trading places. So we're trading places, and so that would be yx. Well, when would we maybe want to do that? Here's an example. If we had 1/2 times 15 times 8. Here's another example where it's like, okay, if I just go from left to right, 1/2 of 15 is 7.5. and then I would have to do 7.5 times 8. And that's trickier for me to do in my head. Like it's going to take me longer to do that in my head if I don't have my calculator handy. So what I would rather do is I can say, well, I can take 1/2 of 8 real easily. That's 4. So let's do the commutative property. So I'm going to do the commutative property of multiplication this time. Because look, it's trading places across that multiplication sign, which is why it's commutative of multiplication. It's trading places over that operation. So now I'm going to get 1/2 times 8 times 15. What's 1/2 of 8? It's 4. And 4 times 15, well, here's what my brain does. I actually know that 2 times 15 is 30, and 30 and 30 is 60. Or you can do, well, what's 5 times 4? That's 20. Put down the 0, carry the 2. 4 times 1 plus 2 is 6. So it's going to give you 60. Anyway, it makes that process a little bit easier. All right, so let's talk about the associative property. Associative property, it's where you can change the grouping. So you're changing the grouping in addition and multiplication problems, and the answer remains the same. Note the order, this is so important. This is like, will help you figure out what this property is. The order of the terms remains the same. Only the grouping changes. That's so important because that's like the telltale sign of associative property. All right, so here's another way to think about it in terms of commutative versus associative. What does it mean to associate with somebody? It means you're hanging out with them, right? Like you're associating with somebody, you're visiting with them. I associate with this group of friends. That's my group of, those are my people. Those are the people I hang out with. So that's the same as the associative property. You're putting terms in a group. You're using parentheses to group them up. So here again is your oversimplified example with the variables where it's like x plus y plus z, and there's parentheses around the y plus z. And I say, oh, let me change the grouping a little bit. How could I change the grouping? Well, I'm going to move the parentheses to the left, and I'm going to use the associative of addition property to do that. Because look, we only have addition going all the way across. I'm going to move the parentheses, and now I'm going to group up x plus y plus z. And is that going to change the outcome of what x plus y plus z is? No, but it could make my mental math easier. So here's how that could work. Let's say you had 1/4 plus 7/4 plus 9. And so this one, based on order of operations, would say, oh, let's take 7/4, we're going to add 9. Let's do that first. Well, you might go, wait a second, that looks confusing, and I would actually rather do this. I would rather group these two together and then add 9. We can totally do that. So because you had that great idea, let's do that. Let's move the parentheses this way. And again, this is the associative of addition property. And so we're going to do 1/4 plus 7/4. We're going to group those, and then we're going to add 9. Something I want to point out, are those terms in the exact same order that we started with? So look at the black. It goes 1/4, 7/4, 9. Look at the next one. 1/4, 7/4, 9. The order of the terms remains the same. Only the grouping changes. That is so different from the one up here. That is like the exact opposite, right? Commutative, they change places. Associative, do they change places? No, they do not change places. The parentheses moves. Only the parentheses moves. The terms stay in the exact same order. All right, so let's finish our problem because we can totally do this now. 1/4 and 7/4, that would give us 8/4. Whoops, gotta turn my pen on, Liz. That's gonna be 8/4 plus 9. Well, we know 8/4 is 2. 8 divided by 4 is 2. 2 plus 9 is 11. That was so much easier to do. All right, well, let's look and see what the associative property looks like for multiplication. Here's your oversimplified, where we've got x, y, z. What would be a way to change that with the associative property? Let's move our parentheses this way. And then we would end up with, I'm kind of writing it over here because I'm running out of space on this. Then we would get xy times z. And again, look at the order. This one was xyz. This one is xyz. Only the parentheses changed. That's the associative property of multiplication. And again, it's associative of multiplication because that's the operation that's occurring between all three of the terms. So let's look at an example where that would actually be helpful. Let's say we had 2/3 times 9 times 1/2. Let's say we had that. So what that would mean is that 9 times 1/2 is 4.5, and then we'd have to take 2/3. That's gonna be a lot trickier to do in your head. But what I see is that, okay, if we leave them in the exact same order, but I just wanna change my parentheses. And I'm gonna go like this, 2/3 times 9/1 times 1/2. Let's see if this makes that easier. So 2/3, I know that 9/3 is gonna give me 3, or you can multiply straight across, right? You can do 9 times 2, that's 18. 18 divided by 3, it's gonna end up giving you 6. So then we're gonna get 6 times 1/2. What's half of 6? It's 3. Perfect. That was so much easier to do. That's when those properties come in real handy. All right, let's talk about what the identity property is. The identity property for addition is where you add 0. Adding 0 to a number does not change the value of the number. And for the multiplicative identity property, or the identity property for multiplication, is where we multiply a number by 1. Multiplying a number by 1 does not change the value of the number. What do they maintain? They maintain their identity, which is why they're called the identity properties. All right. So that's like if we have x plus 0, what does that equal? It maintains its identity, it equals x. Same thing if we had, I don't know, -15 plus 0, what does that give us? That gives us -15. If we had x times 1, that's going to give us x. If we have -2/3 times 1, what do we get? We get -2/3 because it maintains its identity. Our last property, our property of distribution, or it's your distributive property. Multiplication has a distributive property over addition and subtraction. Over addition and subtraction. So let me show you this. One kind of basic example. I want to show you how this looks different because I've had students get confused between this property and associative property because they both start with parentheses. Look at how I want you to see if you can figure out how they're the same and how they're different just in how they start, like right here. How are they the same? How are they different? They're the same. How I see they're the same is that they each have 3 variables in the examples I've given you. In this one, you have x plus z or y plus z, and here I have b plus c. But what about here? What's the operation right here? In this example, it's addition. What is it here? It's multiplication. That's where it changes. So I want to show you something that it is not, I repeat, not possible for you to go, oh, I'm going to change your parentheses and go like this. And then I'm going to get a, b, and then I'm going to get plus c. That does not equal that. That is not how that works. So let me show you how it does work. The distributive property says take A, and we're going to multiply it by B. And then we're going to take A, and we're going to multiply it by C. So then that equals AB plus AC. And that would be your answer. And that is true of over subtraction as well. So if you had B minus C, you would get, we're going to distribute, you would get AB minus AC. So let's try with a different example. So if we had, let's say we had -2 and we had x plus 4. So we're going to distribute that -2 in. So it's going to be -2. And then we would get -2x. Negative times a positive is going to give me a -8. And then if we did -2 times x minus 4, it's going to be real similar. We're going to distribute again here, and we're going to get -2x. Negative times the negative, what happens when bad things happen to bad people? We kind of like that. Okay, plus 8. And there's your answer. So that gets us through our properties. I'm going to go through some examples of combining like terms, and then I'm going to stop this video, and then I'm going to record another one, and I'm going to help you with some of the examples on the workbook pages once we get back there. So here's some combining like terms examples for you. So first one, if we've got -4 plus 7, and then we're multiplying by 1 minus 3m, let's go ahead and see what we can do. So this one, I look within the parentheses right here, and I'm saying, can I combine those? No, they're not like terms. They don't both have an m on them. And then I've got addition here and multiplication here. So first I want to multiply. So let's do 7 times 1 and 7 times -3m. So then I'm going to get -4 plus 7 minus 21m. Now you look across and you see, well, how can are there any terms I can combine? Yes. And then how do I write it in alpha descending order? Well, I'm going to use my commutative property, and I'm going to bump -21 to the front. And I'm going to write -21m. And then I'm going to do -4 plus 7 is going to be +3. And that's your final answer for that one. So let's do a couple more examples. So number 2, we've got -2n minus the quantity of 9 minus 10n. And on this one, same thing. We're going to distribute that negative. We're going to say -2n minus 9. Negative times the negative should be a positive. And then we're going to combine our like terms, because you're thinking about how can I combine like terms and write my answer in alpha descending order. So I'm going to combine my n's first. -2 plus 10 is going to give me 8n. And then I've got the -9 by itself. And there's my answer. So I've got 3 more examples for us. So number 3, we've got -10, 1 minus 9x plus 6 times x minus 10. And you should pause the video and see if you can do this one. I'm going to give you the answer so you can see if you got it right at the end. It's 96x minus 70. And then I'm going to go through it too. But pause the video and see if you can get there on your own. All right, here we go. I'm going to first distribute. There's nothing, by the way, I'm checking. Can I combine these two? No. Can I combine these two? No, they're not like terms. So let's distribute that -10n. I'm also going to distribute the 6n. So then I'm going to get -10 plus 90x plus 6x minus 60. And that's just from me distributing. Now I'm going to simplify and combine like terms. I'm going to lead with my x term. So that gives me 96x. And then -10 minus 60 gives me -70. And there's your final answer. All right. These next 2 are working on us rewriting them in alphabetical order and then in descending order too. So number 4, we've got 1a minus 2ab plus 3ba minus 4b. All right, so first what I want you to do is go through every single term and see if there's anything you can do to make it in proper form. And so this first one, the 1a, I'm just going to write it as a. If you don't do that and you prefer writing it as 1a, that's totally fine. I'm gonna look at my next term. That looks good. I'm just gonna rewrite it. Look at my next term. Something wrong here. I'm wanting you to look at if it's all in proper order, and it's not. We need to flip these two around. So let's put that in alphabetical order. So it's going to be plus 3AB, and the last one is good. So now look across and think alphabetically, which one's going to come first? I've got an A term, an AB term, another AB term, and a B term. Alphabetically, the single A will come first. So I'm just going to rewrite that one. There's nothing else for me to combine with it. So I'm going to have A. And now these two are like terms. They both have an AB. They're both raised to the first power. It's A to the first, B to the first, A to the first, B to the first. So let's combine them. -2 plus 3 is 1. Am I going to write 1AB? No, I'm going to write AB. Again, side note, if you wrote +1AB, it's fine. You're not going to get counted off. You are not going to get counted off. Make sure you heard that. All right, and then finally, we've got our last one, -4B. All right, last one, number 5. So we've got 5 VU minus U squared minus 4UV squared plus 2U squared V minus V. Make sure I wrote that down right. Minus 4, that looks good. All right, let's take it. So let's look through and see if we can figure out, like my brain right now is scanning, for terms that we're going to be able to combine and for how to sort them into descending order. And so far, I don't see any terms that we're going to be able to combine. And I do see that we're going to need to trade these two. So that'll be 5UV. So I'm just, because I don't want to rewrite everything else because everything else is in good order, I'm just going to write it above it, 5UV, like that. And then I look through and say, I don't have any other like terms. I've got a UV, a UV, a UV, but none of them are raised to the exact same power. U is to the first, V is to the first. This one is U to the first, V to the second. And this one's the reverse of it, U squared, V to the first. So there's no like terms. So then the next thing I have to look at is alphabetically, which one is going to come first? Which one in your filing cabinet, like I'm going through all the files in my filing cabinet, which one's going to come first? Alphabetically, it would be this one, the U by itself. So then we're going to have -U squared. And then the next ones, you have to sort them out. We've got UV, UV squared, U squared V. Alphabetically, they are all the same. They're UV, UV, UV. So now you look at the power and you say, which one of the U's has the highest power? And it's this one. So that's the one I'm going to write down next, plus 2U squared V. And now I'm looking between this term and this term and look at the U's. They're both U to the first. So now go to the V's. V to the first on this one, on 5UV, and V to the second. Which one comes next? It should be this -4UV squared. So then that means I'm going to go ahead and write plus 5UV. And then finally, I'm going to write down that -V. And then that is your final answer. So that one was a pretty tricky, involved one. We don't normally give you that many terms to have to sort out, but we wanted you to think about all those different pieces. Okay, so that's it for this video. And then the next video, I'm going to go through a bunch of examples from the workbook to help you guys out with that portion as well, because it can be kind of tricky. All right, thanks for tuning in.